Welcome to the lecture 3. In this lecture, we will try to assign meaning to the propositional formula which we constructed in the previous lecture, which we call semantics, assigning meaning and semantics to the syntactic objects we have. Then we will see truth table as a method for deciding a formula is satisfiable or not. So let's see these ideas together. So first, let's see semantics. And semantics in any context, what it means is assigning meaning to terms what you are talking about. So what happens first? First happens is what is your domain of word of meaning? Okay. So you assign each variable, each proposition, or each statement some value which is either 0 or 1. So you can potentially assign two values. In your interpretation, you can say that 0 is false and 1 is true. That may be your intuitive, innate emotional response, but it is not necessary. To mathematics to work, these two symbols has to be distinct. So what is a model? A model is a function which assigns every variable in your system 0 or 1. Notice that it assigns value to each variable. Why so? Because you do not want to, in a situation, you create a model that satisfies, which relates with some formula, and you take this model and connect with another function, and then you realize the variables are missing and somehow there's a mismatch, and then you need to have a mathematical comparison notation, which variables are mapped or which are not. To avoid that, basic definition of model says that it assigns value to each variable. So here's an example. In this case, we will write like this. When you say p1 variable is assigned value 1, and p2 is assigned 0, and p3 is assigned 0, and so on. Okay, this is a model. Since variables are countable, the set of models is not empty and infinite. A model M may or may not satisfy a formula F. Okay, so this is a notation we are about to introduce, and satisfaction relation is usually denoted by this kind of notation. Okay, when M is a model and F is a formula, and we write this symbol and we say M models F. So how do we really define this model? What is how are we going to know that a model satisfies a formula or not? So here's a definition. Okay, so this is a smallest relation such that every model satisfies the true formula. That must be true, right? If model satisfies the formula P, okay, if on that variable P, MP is 1. Okay. If model does not satisfy a formula F, then I can say M satisfies not F. Okay. If I want to satisfy a formula with F1 or F2, then I have to make sure that M satisfies either F1 or F2. Similarly, we can have interpretation for conjunction, which also requires both of them satisfied, and we can see that how we can roll out for the XOR, implication, or equivalence. It's just unfolding of their intuitive definitions. Okay. Notice that we have no mention of false in this. Okay, so false was not even mentioned. So that means by absence we know that M does not satisfy model, because we are looking for smallest relation. Okay, so the way things are set up, M cannot satisfy false. So now let's suppose I give you a model M and I give you formula something like this, and how do I going to know that this model satisfies this formula? The method is you draw the process and then bottom up start assigning satisfaction relations. Okay, for example, I know that model M satisfies P1. Okay, model M does not satisfy P3 because P3 is 0 and P3 is true. then only it will satisfy here, but M is not. Since this is a conjunction, then therefore M does not satisfy this thing. Now let's look at here P2. M satisfies, no, not satisfies P2. But if you have a negation here, then M satisfies. Okay. Now we need an equivalence here. So this equivalence does not hold. That means M does not satisfy this thing. And in this case P1 M, okay, wow, so this case you have P1 M satisfies. Okay, so M satisfies this guy. Now we have P1 is satisfying and this whole thing is not satisfying, therefore M does not satisfy. So this kind of bottom of traversing of the parse tree, you can figure out a formula is satisfied by a model or not. What we can say in our language, in English, that M satisfies F if M models F. Okay, F is satisfiable if there is a model M such that M satisfies F. Okay, so in this kind, if somebody says F is satisfiable, that person is not telling you which model. Is saying that there is some model. F is valid if for each model M satisfies F. There is no model which can potentially does not satisfy. Okay. F is unsatisfiable if there is no model M such that M satisfies. Okay, so this is called unsatisfiability. So let's do a little bit of an exercise. Let's suppose F is sad. So what do we know about not F? Yeah, what do you think? It's unsatisfiable, or it's a valid, or it's satisfiable. Okay, think about it. If F is valid, then not F is, what do we know about it? Well, if F is valid, then every model satisfies it. So none of the model can satisfy F. Therefore, F is clearly unsat. Okay. Now let's look at the third possibility. If F is unsat, then not F is valid. Okay. A valid formula is also called a tautology. So you may sometimes see people using the phrase tautology, which is equivalent to the word valid. So it is good to know. Now let's focus on this model symbol. Okay, this is called model symbol, and often it is overloaded. So it's how, and many ways it can be overloaded. Here is a one way of overloading the symbol, is that instead of writing one model, you write a set of models. Okay, so and if set satisfies F if for every model occurring in this M satisfies F. Okay, for example, here this is P or Q, then this model P Q both 1 and P is 1, Q is 0 satisfies this model. This formula. Furthermore, we can overload more. Okay, and this is really gets creepy. Okay, so now I am saying instead of left hand side writing models, I am going to write formulas. Okay, and how would I going to interpret this thing? I will say that each model M, okay, that satisfies each formula in M, sigma. Okay, so sigma is not a formula, it's a set of formula. Each model M satisfies each formula in sigma. Collect those models, okay, and each of those must satisfy F. Okay. So we usually read sigma implies F. Okay, and if you in a special circumstances is G is in a singleton set, then we can write G implies F. Okay, it gives us a feeling that this is happening, and that is true. Okay, but you may formally try to prove it. Okay, so for example, you can say that P comma Q implies P or Q. So let's have more definitions, and we say that F is equivalent to G if for each model M M satisfies F if and only if M satisfies G. For example, these two formulas, which basically stating the associativity of a simple disjunction, and says that no matter how you pair the parts, you're going to get the same result, and therefore this is equivalent. Now it's a slightly different definition, and you may not have seen this before, so pay attention. Okay? So this is, if two formulas are equisatisfiable if F is sat, if and only if G is sat. Okay, so this is a bit weird statement. So what happens is, usually somebody gives you a formula F and you do something and it produces another formula G, and then you say these two formulas are equisatisfiable. That means that the transformation you do preserves satisfiability. Okay? If there was a model in one formula, then there is a model for another. If it is not in one formula, that's not another. And similarly, you can define something called equivalent. However, this equivalent concept almost never occurs in practice and useless.